So today we're going to talk about phase, speed of sound, and the Doppler effect. Our objectives for today is we want to learn what phase is. We want to calculate how far out of phase a wave is, how a longitudinal wave travels. We want to learn about the speed of sound and how to calculate it. And we're going to talk, if we get to it, a little bit about the Doppler effect. Phase. All right. An example of phase is two waves can be in phase or they can be out of phase by a certain extent. Now the two waves that I'm drawing right here would be considered to be in phase. These two waves here would, trying to figure out what here we go. These two waves right here are not in phase because their crest and troughs are not matching up. Here we have a crest and a crest, a trough and a trough. So these two waves are in phase. They are the same length and they're matching up with each other. Over here, these two waves are not in phase. Notice I have a crest and directly below it I do not have a crest. A trough, and that's not a trough. So these two waves are not in phase. So two waves, for them to even be close to being in phase, they have to have the same period, which means they have to have the same wavelength or the same frequency. Not necessarily. What we're really trying to compare here is where the crests and the troughs, and are they directly above each other. We've got these two waves, or in this case we have these two pendulums. One is 0.3 seconds behind the other, meaning that it lags a little bit behind. Ways to express the phase. All right, we can do it by fractions. We can say that it would be 0.3 over 1.2, which is 1/4 of a cycle behind, or 1/4 of a period behind. We can do it by degrees. We can take 0.3 divided by 1.2 and multiply it by 360 and say it's 90 degrees behind or out of phase. And that would be ways that we would express how something is out of phase. Okay, in this problem here, it says, what is the frequency of a wave if 2 points are 90 degrees out of phase and reach their peaks 0.1 seconds apart? Well, that means it's right here. I've drawn, there is this, the top one, we'll say A reaches its peak at a certain time, t equals 0. The second one, B, reaches its peak up here at 0.1 seconds. Well, what I want you to realize is every one of these divisions I have here then would represent 0.1 seconds. That means this right here is 0.1 seconds. That means this right here is 0.1 seconds. It's always going to be 0.1 seconds for all four parts of this wave are going to be, it's going to take that much longer for it to get there. Well, that means we can add all four of these times up and find out that the period in this case is 0.4 seconds. So then we know the frequency just has to be the inverse of that. So the frequency then turns out to be 2.5 hertz. Alright, specifically now sound. We're going to talk about sound and what type of waves, how does sound travel. Sound waves travel through longitudinal waves. A longitudinal wave, it's usually when we talk about waves we give you what we call a transverse wave. The sound doesn't travel through that. Sound travels through longitudinal waves. And if you think about a tuning fork, right, we've got this tuning fork here. Yep, we want here you go. If you think about a tuning fork, when these tines are in, what that does is there's no vibration here. And then when the tines go out, it compresses the waves around this. And as this repeats, there's going to be this part where the waves aren't, or the air is not compressed, and there's going to be this part where the air is compressed. And this is a longitudinal wave. What we're showing you here is when the forks are in, it creates a dense area. All right. When the forks are out, it creates a rarefaction, a low pressure zone. So what we have here, all right, is these right here, these areas right here, I'm going to highlight here in yellow. These areas right here are what we'd call rarefactions. So it's low pressure zone. This process repeats itself and the waves are spreading out. Particles are traveling parallel to the waves. This bottom part down here is very, very important. Particles are traveling parallel to the waves in longitudinal waves. Notice here that as I look at our picture up here, things aren't moving up and down. All right, the tines are moving in and out, in and out. So they're going to be moving parallel. Right, the tines are moving in the same direction that the waves are moving. Right, there'd be a particle. So if you think about the tines being the particles, they're going to move left and right. They're not going to move up and down. Sound and air. All right. Well, the first thing I want to point out to you is our equation down here. The velocity of air, or the velocity of the speed of sound in air is 331 meters per second plus 0.6 the temperature in degrees Celsius. So what this tells us is speed in air is related to the temperature. It's independent of the instrument. For example, the speed of sound from a guitar is going to travel the same as the speed of sound from a ukulele, whatever that is, or the speed of sound from a piano. Different instruments don't project faster or slower sound. The speed of sound is the same for all instruments. What it does depend upon is the temperature. And what we find out is because it's plus 0.6, whatever the temperature is in degrees Celsius, is that sound will travel faster in warmer air. So let's do a problem with this. How fast will a wave travel in air at a temperature of 15 degrees Celsius? Well, this is a simple math problem. We get 331 plus 0.6 times 15 degrees. This turns out to be 331 plus 9, or the velocity in air when the temperature is 15 degrees Celsius is 340 meters per second. Alright, this takes us to the Doppler effect. And with the Doppler effect, what I want you to realize is the Doppler effect is when you hear a siren. For example, the ambulance coming at you, you hear a high-pitched sound. When the ambulance is going away from you, you hear a low-pitched sound. The question becomes why? Well, when the ambulance is coming towards you, the frequency is going to increase. All right. So as we see this frequency increasing, you're going to get a high-pitched sound. As it's going away from you, the frequency is going to decrease, and you get this low-pitched sound. Well, the reason you're getting that difference is you're standing somewhere. I'm just going to draw a picture of an ear. And if the siren were to be standing put, so here's this siren, and it's got this sound that it's putting off. So you have these sound waves. And notice that we are showing this as a longitudinal wave because sound is a longitudinal wave. You hear a certain frequency, meaning you're going to hear a beat every so often, and that's the frequency. But it's also in the same direction the other way. The frequency, the distance between these beats is the same on both sides. But what about if it's traveling at you instead of just standing put? Well, what happens then is we have this, and we have this sound come out. Because it's moving forward, these sound waves get closer to each other, and you're hearing more beats now. Because it's moving away from where the last one was, you have less sound waves behind. So when it's moving towards you, and this is why you're going to get a high-pitched sound as it travels at you, and you're going to get a low-pitched sound because you have a lower frequency when it passes you. I'm sure you'll have some questions about that. We got some videos we'll watch, and I'll see you on the flip side.